Okay, we're going to talk about something called the dot product of two vectors. Okay, let's say I had the vector 3 comma 8 and the vector 2 comma -2 comma 4. So I'm going to graph both of those from the origin. So 3 8 would look something like this, and then -2 4 would look something like this. Just for fun, because we like to have fun, how long are those vectors? What's the magnitude? So if I called this u and this v, what is the magnitude of u and the magnitude of v? We're just going to use the Pythagorean theorem. So the square root of 3 squared plus 8 squared. So u is 8.5 units. And then I don't need to worry about the negative when I'm finding magnitudes. So I'll just do the square root of 2 squared plus 4 squared. And I get 4.47. Okay. Well, there's another operation called the dot product. Did you guys do that in physics? No? Wow, that kind of surprises me. I've never taken a physics class, so I don't know. Um, and let's call this U1 and U2 and or V1 and V2. Okay, the dot product, vector U, and this is the vector symbol, dot vector V is defined as U1 times V1 plus U2 times V2. And if your vector was a three-dimensional vector, then you would write plus u3 plus v3. If it was a four-dimensional vector, then you would write plus u4 plus v4. And you can have vectors in as many dimensions as you want. You can have a 14-dimension vector. And you can still do the mathematics. Visually, it's kind of hard to draw because we can't really draw anything outside of 3. So in this case, we're going to do 3 times -2 plus 8 times 4. And that gives me 6 plus 32, -6, plus 32, which is 26. Did I do that right? 3 times -2 and 8 times 4. All right, so the dot product is 26. Now, we're not really going to get into what the dot product means, but the dot product is a way of, it's useful in combining vectors, and it's beyond the scope of this class. You just need to know how to calculate the dot product. Okay? Well, what if I had, I'm going to, let's do u is -4, 1, and vector v is 1, -4. Let's do the dot product. What do I get? -4 times 1 plus 1 times -4, and I get -4 minus 4 is -8. Hmm? Yep. Okay. What if u is 3 comma 2 and v is -2 comma 3? I get 3 times -2 plus 2 times 3, which is -6 plus 6 equals 0. Okay, why did that happen? So my first vector is 1, 2, 3, 2 right here. And then my next vector is negative 2, comma 3, which is right here. Why did my dot product end up being 0? It has something to do with the relationship between those two vectors. They do have the same magnitude, so that's one thing. Well, so you would think if vectors were pulling in opposite directions, they would kind of kill each other. But the dot product actually, well, and once again, it's not something that you're going to see. But the reason it happened is because those two vectors are perpendicular to each other. Okay? And what if I made this vector twice as big? What if it was 6 comma 4? Is the dot product still going to be 0? 6 times negative 2 is negative 12, and 4 times 3 is 12. So the length of the vector didn't actually matter. It was just the direction. So whenever one vector is perpendicular to another vector, the dot product will be 0. Why? Don't worry about it today. Well, don't worry about it in this class. Or in Corbin's case, ever. Okay? Now, the dot product is doing a lot more than you realize, but we don't actually say perpendicular when we're looking at vectors, because most vectors are three-dimensional, right? So when we say perpendicular in vectors, we actually say orthogonal. And orthogonal is stronger than perpendicular. Orthogonal means perpendicular in every direction. So if you had a ball, like a basketball, and you had a vector going straight up through the ball, it's actually perpendicular to the ball in every direction, right? If you tilted that vector sitting on top of the ball and you rotated your camera around, eventually you would find one where it appeared perpendicular, right? If I have a basketball and I bend this toward me, to you and to me, the line appears perpendicular. Does that make sense? But if I move my camera over here, then it would be slanted. Do you get that? So orthogonal is stronger than perpendicular. It doesn't just mean perpendicular, it means perpendicular in every direction. But in 2 dimensions, that's not, you can't do that. I mean, it doesn't matter. So you're in the book, you're going to see the word orthogonal, which is weird because we're only doing 2-dimensional vectors, and perpendicular would have been good enough because there's no such thing as, well, orthogonal is not any stronger than perpendicular. So the first set in section 7.2 is perform the dot product, which is really easy. It's just u1 times v1 plus u2 times v2. And then in the next one, it says determine whether, what does it say? Oh, sorry. The third section says determine whether each pair of vectors is orthogonal. That's really easy. You do the dot product and see if you get 0. Okay, well, here's another definition of the dot product. U dot V, and it looks like a multiplication symbol because it is a multiplication symbol. Remember when we did multiplication of matrices? We had matrix A and matrix B, and we made sure that the rows and the columns matched up, and we did this times this plus this times this plus this times this, and it equaled that. That's all the dot product is. It's just matrix multiplication, except you have a 1 by 2 matrix and a 2 by 1 matrix. Okay? So U dot V is equal to the magnitude of U times the magnitude of V times the cosine of the angle between them. So if I have this vector and this vector, the dot product means the length of this vector times the length of this vector times the cosine of theta, which is the angle between them. Well, when the angle between them is 90 degrees, the cosine of 90 is 0, which is why it turns into 0. Okay? Now, one of the cool things about vectors is this right here is equal to u1 times v1 plus u2 times v2. So we're not even going to do dot products the hard way because there's an easy way. And that right there is why we use vectors. Because we can turn a complicated equation into vectors and then do a really easy calculation. u1 times v1 plus u2 times v2 plus u3 times v3 and so on. So this is the whole reason we use vectors. Well, what if I didn't want the dot product? What if I wanted to know how big is the angle between the two vectors? How big is this? What would I do? How do I solve for theta? Divide by the magnitude of u times the magnitude of v. And then do the cosine inverse. So if I take the dot product of a vector and I divide it by the magnitude of each of the vectors, and then I invert the cosine, that will tell me the angle. So let's say this is 6, 1, and then this vector is 2, 5. What is theta? Well, I do the dot product. 2 times 6 is 12 plus 5 times 1 is 5 over got to find the magnitudes. So the square root of 2 squared plus 5 squared is 5.38. So I'm going to take 17 and divide it by 5.38. And then I'm going to divide that by the square root of 6 squared plus 1 squared. What is that? Right, now I need to do the inverse. Carly, where are you stuck? So that's a good point. Thank you. You can either do u dot v divided by magnitude of u divided by the magnitude of v, or you could put this in parentheses and divide them both. So what that means is 12 divided by 2 divided by 3 is the same as 12 divided by 6. So yeah, as long as you put these together, then you can either divide the magnitudes separately or together. It doesn't matter. Okay, so I now know that the cosine of theta is 0.519. So if I invert the cosine, I get 58 degrees. Does that look reasonable? Yeah, totally. Okay, what if I had -4, -6, and then v was, oh, I don't know, 5, -2. What is the angle between those? Well, I need to find u dot v divided by the magnitude of u and the magnitude of v. So u dot v is going to be -4 times 5 is -20 plus -6 times -2 is 12. So that is -8. over the square root of 4 squared plus 6 squared, and the square root of 5 squared plus 2 squared. So negative 8 divided by 7.21 times 5.85, 385. Now what? Take the inverse cosine. Is that right? Well, let's draw it. So 1, 2, 3, 4, 1, 2, 3, 4, 5, 6. And then, does it look like that angle is 102 degrees? Yep, it worked. Okay. So the first set, you're doing the dot product. Second set, you're finding angles. Third set, you're just determining if they are orthogonal, which you just take the dot product. If you get 0, the answer is yes. Okay. And then we get into work done. And we talked a little bit about this last time. So if we have a boat that's stuck in the mud, and we wanted to pull it out, but one tugboat is not enough to pull it out, then we need 2 tugboats. So we decided that the 2 tugboats cannot pull in the same direction. If they do, they're going to hit each other or run over the cable. Okay, but the problem is, the bigger this angle, or sorry, the smaller that angle is, the less force the tugboat actually pulls on the stuck boat. Does everybody get that? So if the boats pull in this direction, then they're really working against each other. Visually, does that make sense to you guys? Okay. So if we want to increase the force, if they're on these green lines and they're pulling and the boat doesn't become unstuck, what do? We change the angle. We narrow the angle. So we can put them right here. And if that's not enough, then we can narrow the angle even more. And the closer they are to pulling in the direction we want, the more force is put on that boat that's stuck in the mud. Does that make sense? So if I had a weight sitting on a bed of ice, okay, and I wanted to move that weight 10 feet, okay, and I pulled in this direction, then I really just have to pull, well, hold on, let me say this correctly. Then the direction I am pulling is the same direction as the direction that I want the weight to move, and so all of my work is being done in the correct direction. It's the most efficient way. That's a good way to say it. Well, we probably won't be able to pull that way. What if we pulled in this direction? Then I would have to work harder. Does everybody understand that? Okay, what if I pulled in this direction? Work harder. What if I pulled in this direction? You're not going anywhere, because this vector does not have an x component. It only has a y component, right? So basically, let's say I had a weight, and I had a bunch of vectors that were 10, that had a magnitude of 10. So each one of those vectors has length equals to 10. Okay? So how far did the weight get pulled on the first vector? 10, because all of my force was going in the right direction. Okay? Well, what if I did this vector. Then if I draw a line straight down, I really only pulled it that far. Okay? And then for this vector, even though I pulled with the strength of 10, I only moved this far. Did you guys do stuff like this in physics? Kind of? Okay. And then this vector has a projection that's up to here, but the perpendicular vector didn't go anywhere. I mean, it may have lifted off the ground, but it didn't go in the direction that we were hoping to. Okay? So, how do we determine how much work has been done? Well, there's a very simple formula. Work is equal to the force vector dotted with the distance vector. Now, this is way more complicated. Well, it's much further reaching than what we're going to do in this class. There's so much information I could teach you on where this equation came from, how it works, and where it's used, but we're just going to graze the surface. So work is the force vector dotted with the distance vector. And if we take a vector and we dot it with another vector, what sort of answer do we get? When I did u dot v, then my answer was a vector or a number. It was just a number, kind of like a magnitude. Right. So work is just going to be a number, but that number is going to combine the units of the force and the units of the distance. Okay? So if I had a weight and I pulled it in this direction with a force of a vector 4, 3, and I moved that, so this is my force vector, and I'm pulling in that direction, and I moved it along a vector 8, 0, how much work did I do? But let's say I'm pulling in pounds, and I moved a distance of feet. So I got a big weight, and I'm pulling, instead of pulling parallel to the ground, I'm pulling at an angle. And how hard am I pulling? Well, 4 squared plus 3 squared equals 25 squared. So I'm pulling with a force of 5 pounds. Right? And I moved it a total of 8 feet. So how long? That's just going to be 8, right? How much work was done? Well, we take the dot products. 4 times 8 is 32, plus 3 times 0 is 0. 32 what? Okay, we'll get to that in just a second. So 4 times 8 is 32. 3 times 0 is 0. 32 foot-pounds, or pound-foots, which doesn't, that's not how we say it. Okay, so how much work did I actually do? I moved a weight according to 32 foot-pounds. But wait a minute, didn't I work harder than that? How hard did I work? 5 pounds per 8 feet, which is 40. So I struggled at 40 pounds, but the movement only accounted for 32 pounds. Why? No, we're pretending we're in an ideal situation because I wasn't working very efficiently. I was pulling at the wrong angle. Right. So I exerted 40 foot-pounds worth of effort, but as far as the movement of the weight, it only moved 32 foot-pounds worth of energy. Does that make sense? So how could I make this more efficient? Change the angle. So I'm going to take a magnitude 5. So let's see. This will be kind of hard. If this is, well, let's actually do it less. Let's do 3 comma 4. That's going to make it less efficient, right? So if I changed my vector to 3 comma 4, I'm still pulling with the force of 5, but now I'm pulling at the wrong at a worse angle. 3 times 8 is 24 plus 4 times 0 is 0. And now I have done the work of 24 foot-pounds. So of my 40 foot-pounds of energy exerted, I only actually did 24 foot-pounds of work. Okay? And how could I make this the most efficient? Pull straight. So what would this vector be? 5, 0. And 5 times 8 is 40, and 0 times 0 is 0, and I end up with 40 foot-pounds. Does that make sense? What if I pull straight up? What would my vector be? It would be 0 comma 5, and when I do the dot product, it all turns into 0, and I didn't do any work at all because I'm pulling in the wrong direction. Okay, does that make sense? What if, let's say I had a comma 1, so a squared plus 1 squared equals 5 squared. So that'd be 25 minus 1, so the square root of 24. So this vector is 8 comma 0, and this vector is the square root of 24 comma 1. When I dot those, what should I get? Well, my number should be close to 40, because I took my original vector and I rotated it down, so I'm closer to a 0-degree angle. So the square root of 24, that didn't work, 8 root 24 plus 0, I'm really close to 40. So if you want to find out how much work is done, you just need to know what direction is the force in, what's the vector of the force, and what is the vector of the distance, and then you take the dot product of those. If you look on page example 4, page 715. How much work is done when a force of 2 comma 4, would be like this. So 2 comma 4 moves an object from 0, 0 to 5, 9. I'm kind of off. Oh, I missed. So 5, 9. So I'm pulling in almost the right direction. How do I find the amount of work done? So this is in pounds and this is in feet. Well, okay, let's do that. So 5 squared plus 9 squared, take the square root. And I get 10.29, and the other one is 2 squared plus 4 squared. So 4.7472. If I multiply those together, the total possible work is 46 foot-pounds. When does that happen? When would we reach exactly 46.043 foot-pounds? When the two vectors are going in the same direction. Are these two vectors in the same direction? Almost. So when I take the dot product of them, 5 times 2 is 10, plus 9 times 4 is 36, and I got exactly 46 instead of 46.04. So the reason I didn't get 46.043 is those vectors are not exactly in the same direction. Okay. So the next one says, this is where it says your turn. 1, 3. Oh, I did it wrong again. 1, 3 moves something to 4, 7. So I'm pulling a force of 1, 3, and the object I'm pulling moves to 4, 7. How much work was done? 1 times 4 is 4, plus 3 times 7 is 21. 25 Newton meters. Joules, right. Does that make sense? Okay. That's it. And really, this is the, well, I guess this is just the intro to dot products. There's a lot more that you'll learn later, but not in this class.